Hey everyone, welcome back to the Rust Review. I'm Brandon Konkle, and this show is where I dig through articles and topics from all kinds of different sources. Things like This Week in Rust, the Rust subreddit, the Rust tag on Mastodon, Discord, fellow Rust stations, all over the place, to find interesting topics to talk about and let you know what I think. If you have an article that you'd like to see featured on the show, let me know in the comments or in the Rust programming language Discord, where I tend to lurk as Konkle. This week's episode features articles on async Rust challenges, developing a secure bootloader for RISC-V, efficient logging, mastering dependency injection, and the story of a confusing phantom memory leak, and more. I'll start off today with Iroh. So Iroh is a project maintained by Rudiger Klein, who authored this article back on July 31st. He works on Iroh, which is a set, like it says here, a set of Rust crates for peer-to-peer networking and data transfer. It has tools for moving data, for syncing state, for connecting devices directly without needing an intermediate server, all of that kind of good stuff. And so he posted this article to talk about the challenges he faced working with async Rust, which I think are legitimate challenges. So first of all, he talks about how he usually advises Rust beginners to avoid async at all until they have a good grasp on the language because, and I can attest to this, Rust can be tricky even for experienced developers. He tends to stay clear of async Rust, but on this project, Iroh, it's built on something that's pretty cool, this Quinn project here, which I'll pull up in a different tab. The Quinn project is basically an alternative to TCP. I know it uses UDP behind the scenes, and so it kind of addresses the shortcomings of TCP, it says on the article here. So it's built based on something with an excellent async API already. And it's something that's very async heavy, basically. It's a necessity in his use case. And so he knew that he needed async in this case. He couldn't avoid it like he typically does. And so the first choice that he was faced with is picking a runtime. And I will say, years ago, this used to be a harder problem. But right now, like he says, Tokyo is pretty much the winner. Tokyo works across all platforms. It's the default runtime, not just for Quinn, the project he based it on, but a lot of other projects. So like he says, it was a natural choice here. But there are definitely criticisms of Tokyo. Tokyo's not perfect. And the problem that he faced was at this point, the alternatives have definitely started to dwindle. He talks about async standard and how he hasn't seen updates in years. Talks about small, who is also not very active. It mentions newer runtimes like Glamio, which I'm definitely interested in because they're based on IOU ring, which is an async API for Linux built in. Which is pretty promising, but it's only available on the Linux ecosystem, not on Windows or Mac. So he went with Tokyo. It was definitely the best option for what they were going for. But with Tokyo comes some challenges, especially based on, I will say, a lot of his criticism around Tokyo is based on the fact that he is working with a synchronous library behind the scenes. He's working with an embedded database called RISCy, which is really similar to SQLite. But you'll also see the same problem in some other REST libraries, really prominent libraries that were created before async was really prominent. So like the Diesel ORM for SQL, that's synchronous, and so you have to wrap it in order to use it async. Or the Juniper GraphQL library. Those are cases where you would face the same kind of problem that he is here, where he needs to interact with synchronous code within the async Tokyo runtime. So one of the most important things when you're writing async code is don't block. Don't use something sync inside your async calls, which would end up blocking the thread. And so he links to this rustexercises.com article about don't block the runtime. It talks about why. It talks about if your task never yields, if it never yields control back to the runtime, the task scheduler essentially, then it's never going to be able to run another task. So this article advises spending less than 100 milliseconds or microseconds. Microseconds. Ooh, that's a big distinction between, I was thinking milliseconds when I first looked at it, but no less than 100 or no more than 100 microseconds between yield points. So when it talks about yield points here, it's talking about the await points. When you're executing code within an async function, you have control. And then when you get to an await point and you're awaiting that, that's when you yield control back to the runtime. So you don't want to spend more than 100 microseconds between your yield points if you want to avoid clogging up the tasks queue, essentially. And so that's what he's really concerned about here with Iroh. So the common pattern that he reached for at first is to use a handler thread, use a separate thread outside of the Tokyo runtime for your synchronous library. So RISCy in his case. That is really common. That's, you see, what is it, diesel async and things like that. That's the strategy that they use in order to communicate with the synchronous thread. So that's the approach that he went also. And he went with an approach that's really familiar if you're in the Go ecosystem. He used a separate thread with communication via channels. So instead of any kind of shared memory that requires really rigorous synchronization, he went with a channel approach and used a library called Flume, which offers a good set of tools around channels for inter-process communication. Flume is a good one, but he points out a little bit later on in the article that he faced some challenges with that too. So let's see. Oh yeah, the next thing that he was talking about, one thing that they've started doing as an alternative to this separate synchronous thread is actually having a separate thread that has another Tokyo runtime running. So you've got your main Tokyo runtime in your main thread that's providing most of your operations. And then you've got this separate thread with a separate runtime managing just this single threaded environment for all of the blocking tasks that you want to do within that synchronous thread. But in this way, you can still use Tokyo to manage that. You can still use these lightweight tasks like he's talking about. So that's an interesting idea. I definitely want to know more about the benefits of that over just simply communicating with the synchronous process in another thread. But then he goes on to talk about reading files, file IO, and the big problem that he faced with RISCy, which I think a lot of other embedded, a lot of synchronous processes are like this, it's not send, meaning you can't send it between threads, which is obvious. It's synchronous. It's not intended for multi-threaded use. So it doesn't implement the send trait. So send, as you may know, is often paired with sync. Send and sync represent the ability of processes to be sent or values to be sent between threads. And so that was one of the challenges he faced here. RISCy is not send, which makes sense. So he's got the separate thread pool to spawn worker tasks that will interact with this synchronous database thread. And he goes on to talk about some of the problems that he faced with panics. So yeah, that I see what he was saying here. So he's saying that if you've got a non-async or just a sync, a standard function, and you're interacting with the normal standard library tools like standard IO, then your functions return a result. If it's something that could error out, then it's going to return a result, and you can safely call it without having to worry about the possibility that it could panic You can just resolve the result. You can use the little question mark operator to, as syntactic sugar to handle either unwrapping the result or returning the error case for the result. And so you don't have to worry about it just suddenly panicking out from under you. And that's one of the great things about Rust. It can mathematically guarantee in the compiler level during build that it's not going to just panic. But in Tokyo, it's a little bit more nuanced than that. It's not quite as straightforward because you have to understand a few things about it. If a function, or he says whether a function panics or not, depends on the state, not just of the entities that you're working with, but on a global or thread local state. So for instance, the runtime that's running in your current thread, things like that, some of that, the context around it could lead to panics. And so the examples that he gives are things like some functions, like Tokyo spawn, it panics if you call it outside of a Tokyo runtime because it has no runtime to spawn in. So there's nothing about the inputs or the outputs that would lead to the panic. It's just the fact that it's been executed outside of the Tokyo runtime. And so that separate global context can lead to a panic that you might not be expecting. Or he talks about spawn local, which panics if you're not inside a local set. So you've got to make sure that you've got that set up. It talks about other things that aren't even dependent on those kind of factors, but are dependent on which runtime you're using in general. So for example, sleep will panic if you're on a runtime that doesn't have time enabled, and some other functions will panic on a runtime without IO enabled. So there's a lot that goes into whether you could see in an unexpected panic in the Tokyo ecosystem. Now, I will contend that these kind of scenarios are generally, they only apply when you're working in a situation like he has, where he has a synchronous thread that he's interacting with separately through channels like this. Like he's spawning things. He's working with multiple runtimes. That is a little bit more advanced. That's not something that you would do every day. And so he acknowledges you could argue that you won't have these issues if you just stay within the Tokyo runtime all the time. But in his case, he needs to interact with blocking IO. It's not something that he can avoid in this case. So he goes on in a little bit more detail on how to work around that. Talks about more about panics, which this was something that I didn't know about. There are cases where Tokyo can actually swallow a panic, because if there's a panic inside a Tokyo task, it might just get hidden away, captured by the runtime and converted into this Tokyo join error. And so if you don't use the join handle that you get back from it, then you might not ever know that thread panicked. So I like in the article, he has recommendations on how to work around all these things, how they have worked around all of these things for Iroh. So I'll skip ahead a little bit here and talk about another thing that I wasn't aware of, the futures crate. And the futures crate is a pretty common tool to use when you're interacting with async functions. Gives you a lot of tools to work with it, but some of the combinators that it provides, that's the utilities that it gives you to work with any kind of async function, no matter what runtime it's on. Unfortunately, they're buggy. He says that there are some cases where it has trouble, and because it uses a lot of unsafe markers, they weren't confident enough to fix it themselves for Iroh. So after dealing with the trouble that they've run into, they decided to take the drastic step, as he says in his article, to stop using the futures crate altogether and use a different set of crates to replace it. So they have a futures light crate and a futures unbuffered crate. Futures buffered crate that they're using to replace what futures was giving them. So basically he's frustrated because there's not one high quality, well-tested place to find all of the combinators that you need to work with async functions. And he ended up having to do some of his own, which is valid criticism. That's something that I would not have expected from the Futures Crate, especially with how widespread that it's used. And then further on in the article, he talks about why they replaced Flume. The big situation around Flume was that send is not cancel safe at all, which he said he could deal with. That's a performance optimization. He's okay with send not being cancel safe, but receive is something that they needed to be cancel safe so that they're not missing messages. So, and he points out that Flume is casually maintained. It's not something that somebody is committed to providing support on, which is okay. I mean, it's an open source project that somebody's giving away for free, but it's definitely part of the consideration that goes into this. So along with the future stuff that they had to write, they also had to find an alternative for Flume, and they ended up using async channel. But apparently it's still not what he was looking for, but at least he was able to find an alternative that worked to do what he wanted it to. So ultimately, he wraps things up by talking about his wish list for the future, what he would really like to see happen to smooth over some of this difficulty. And first and foremost, he calls out a protective wrapper around Tokyo that prevents you from being able to access the global spawn blocking, and spawn local functions. And he says instead of using these global functions, spawning tasks should be from an explicitly passed runtime handle. So Tokyo could return a runtime handle. Here's the handle for this running runtime, or this runtime that's in context here. And so with that handle, you could have type parameters that encode what it can support. So things like if this runtime handle doesn't support time, then that's a clue that the compiler could use to say, hey, you can't use sleep here. And so at the build phase, it could disallow the use of sleep because this runtime handle doesn't support time, or something like that. And then he also talks about local tasks. Local tasks are the ones that don't support send, so they have to stay on the same thread, and kind of prioritizing support for them and making them a first-class citizen is another thing that he would really like to see. So yeah, ultimately, it was a very informative article. That was interesting. There were some things that I didn't know about how Tokyo works here. And I think it was a great criticism of where we're at in async Rust right now. Async Rust is still relatively new, even though we're seeing, like I talked about, Tokyo emerge as the clear winner. It's not fully battle hardened in some ways yet, and so, especially in edge cases or unusual or advanced cases like he was talking about there. I still think it's really good though. Tokyo's efficiency, the task scheduling approach that it uses is highly optimized. I think it's production ready, but be careful about some of those edge cases that might bite you if you're using it in less common ways, I guess. Next up is an article by CodeThink. This is from Lawrence Hunter at the CodeThink blog, posted on August 2nd. And it is all about bootloading in RISC, or RISC-V specifically. So RISC-V is really similar to ARM. In fact, ARM is a type of RISC implementation. It's a proprietary RISC implementation. RISC itself means reduced instruction set computing, and ARM means an advanced RISC machine. That's what ARM stands for. But RISC-V is another alternative to that, an open source alternative to ARM that provides reduced instruction set computing. And so what RISC is the future. It's a modern CPU architecture. In our x86 and x64 architectures that we have now, there's a lot of cruft. There's a lot of leftover stuff from the 70s and 80s and 90s in there that we don't really need anymore, that aren't really used anymore, but it's there for backwards compatibility. Anything that was built for that architecture should be able to continue running on that architecture. Similarly to the approach that I talked about that Rust takes for for its backwards compatibility. That's what x86 and x84 use as well, that approach to backwards compatibility that gives you confidence to build on that platform. But it is it's not ideal in a lot of ways. It uses a lot of energy. It's not very efficient. You've seen mobile devices and the latest like M1 and M2 chips from Apple on the Apple silicon platforms that are embracing ARM, that are embracing that type of RISC for cutting out the cruft, cutting out the old parts of the CPU architectures that aren't needed anymore, to streamline it, to make it more energy efficient, to provide all kinds of benefits. So RISC definitely is the future. I think Apple has proven that with the Apple Silicon. And so RISC-V is a non-proprietary and open source alternative to supporting that same kind of platform. So this article from Lawrence is about writing a bootloader for RISC. So a bootloader is the thing that bootstraps your system. When you turn it on, something has to get things rolling so the operating system can boot up. And so that's what the bootloader does. And the more commonly used bootloader in RISC-V is one that he calls out called U-boot. And so you'll see him compare his Sentinel boot, which is his alternative to it, with U-boot, the more common use in a lot of cases. And one of the big downsides, one of the shortfalls in U-boot is that it doesn't have a way to cryptographically verify the integrity of that kernel, the core that it needs to spin up. So he talks a little bit lower down in the article. Yeah, he talks about the threat model here. I think this is a good thing to think through before we're jumping into the rest of it. The idea is that you want to know that the kernel that you're loading is definitely the kernel that was intended for you by your vendor, your source. So, for example, if you're booting up a Linux kernel, then you want to know that the Linux kernel that you're using hasn't been tampered with, because it's intended to be used on thin client devices. So devices that they don't store their own OS. They use over-the-air updates. There's a chance that, given as he calls out, social engineering attacks or evil maid or man-in-the-middle attacks, there's a chance that you could get an OS payload that has been tampered with to try to steal information or gain control or whatever it wants to do. And so what he's wanting to do is verify that this payload that Sentinel Boot is loading, it hasn't been tampered with. It does indeed come from the source that we think it does. And it does this through... where is it down here? I'm skipping around in the article to find. Yes. So it does this through public key cryptography. So this is the same kind of strategy that you see in JWT tokens, or some people call them JOT tokens, but I don't like that. But it's the idea that you encrypt a portion of the payload or the whole payload. A lot of times in JWT tokens, you'll just create a signature of the payload by hashing the payload and then signing that payload with a secret key that only the vendor that's providing you the payload and your system that's executing the payload, only they know the secret key, so they can verify that it's been cryptographically signed correctly. So like in a JWT situation, you would have a pre-shared key between the auth provider and the system that's running. And it gets really complex, but basically that's what he's wanting to do here. He's not necessarily encrypting the whole payload, but he's encrypting a hash of the kernel. So with this secret key, you can verify, okay, this kernel that has been hashed has not been tampered with, and we really are booting up what we think we are. So in order to accomplish this, he talks about basically the difference between system level code and typical REST code that you would run every day. So This kind of goes into a little of what I was talking about in the CrowdStrike situation last week, where if this system level code is running in kernel mode, essentially that's what we're talking about here, because it's booting the kernel. And so a lot of the strategies that you would use in other languages to approach this kind of fall short. Because they rely on runtime checking. They rely on things that would provide overhead that's just not acceptable in systems code. He talks a little bit about that further on in the article. Yeah, I'm jumping around all over the place, so I'll go back up to where I was. But basically, he points out that Rust is a language that hypothetically could overcome that because it doesn't need runtime checks. It provides enough constraints that the compiler can handle all of that at build time. So that's where it leads to the zero cost abstractions that Rust is always talking about, because it doesn't need a runtime supporting it and providing overhead to do it. But he also points out that even in 100% safe, non-overruled, so no unsafe specifiers anywhere, no overrides, no turning off those protections, you can still see a vulnerability. It's not 100% perfect, and that's something that we should acknowledge here. Yes, Rust is great, but even when all the protections are in place, it's not 100% perfect. There's always going to be more that we can do to close things up. But the strategies that Rust uses, the ownership, the borrowing of values, the lifetimes of values, those kind of things really make it much more likely to be safe and much less likely to contain the kind of bugs that we worry about here. So that's why they were looking at Rust. So they talked about the threat model that I already mentioned, and then they go into what's it take? How do you do this? This is in a Linux. I believe this is in a Linux context. Yes, because he's talking about formatting them as ELF binaries. That's the binary format that Linux uses. So first, you've got to link the binary into an ELF format that can be executed in a Linux context. And then you need to write some assembly code to initialize the hardware. So he shows a diagram of the control flow and everything, but one shortcut that they used in this project was to go ahead and take advantage of U-Boot's TFTP operations. It's a type of simple FTP. So instead of re-implementing that, he's writing some assembly code to handle that. But at that point, after all that's done, then we've now jumped to the Rust entry point. So this is where you normally breathe a sigh of relief because it's typically memory safe. But the next two steps from here are initializing a serial driver and a memory allocator, and they both require a lot of unsafe work. So you're not out of the woods yet. You still have to use the unsafe keyword to override the protections. But once you're done with that, once you're through that, you finally are, you have emerged into truly safe Rust. So he's got some great diagrams on how they did it. He talked about supporting dynamic memory allocation using a custom implemented allocator by implementing this global alloc trait. So even though he implemented his own memory allocator, he did it in a way that is interoperable with other things. So advanced data structures, like he talks about, that's actually the requirement in order to use more sophisticated or complex data structures rather than just your really basic primitives in Rust. I thought that was really interesting to hear about. Like, these are some of the underpinnings that we use every day. He talks about implementing a doubly linked list for his memory allocator. And this allows, like he says, bidirectional traversal. But in order to do so, you need to have mutable pointers. These are mutable pointers, and in order to have a forward pointer and a back pointer, you would have two mutable pointers. So that's not something that Rust typically allows. But he said he could still do it, but using a little bit of indirection through a mutex to enforce synchronization. So that did allow him to use the forward and backward references, but they just have to be locked and unlocked when they're used, so that you can't mutate a reference from two different places at the same time. that's part of the protections that Rust provides, and the mutex is the fact that it's necessary is a distinctive of Rust, I think. You might have mutexes in other languages like Go, but you don't always have to use them depending on the situation, and you can get away with not using them. But Rust enforces it. You need to. You can't have two mutable references without it. So next, he talks about implementing that cryptographic check. So he's hashing the kernel using SHA-256. He talked about the avalanche effect. So if there's what is it? I can't remember exactly how the avalanche effect filtered in. Oh, yeah. So you need to be able to determine the size of the kernel from just a pointer, because including even in single extra memory locations should completely change the result. And in SHA-256 it does. And that's the avalanche effect that he links to in a nice Wikipedia article here that goes into more detail about that. I learned about that a long time ago, but I don't remember much about it. So in any case, he talks about how they implement the signature and talks about how the way that it works, just like in a JWT context that I was talking about, you can't sign the kernel without that private key. And then if you tamper with the kernel, the hash isn't going to match. So this ultimately leads to being confident that this is the payload that it was intended to be. All right, so the rest of the article is really interesting. He talks about how he's testing it. He's talking about the analysis that he does compared to U-Boot. And it's a really fantastic article. I would definitely check it out if you want to know more about some really low-level operating system procedures like this, and how you can go about implementing them for modern platforms like RISC-V in Rust. It kind of addresses some of what I was talking about last week about in the Windows environment, at least, we don't totally know what this looks like yet, or I haven't seen a lot of good examples for this, but this would be an example in the RISC ecosystem instead, and I found it really fascinating. Next up, I'm going to talk about efficient logging. This is an article from Tony Baratzis. I'm probably pronouncing that wrong. I apologize. But he's a student at the University of Technology in the Netherlands. And he posted about logging and standard out considerations that I had never really thought about. And it's much more complex than I would have originally thought. So Tony's article introduces his conundrum, how he got to this realization of how complex logging could be and what you have to do to efficiently manage it, and how much impact it can have. Like it's surprising how much overhead logging can add. But he's been using a really neat command line tool called Ouch. Now, I would think with a name like Ouch, it's about error handling, but it is not. It's actually about compressing and decompressing all kinds of different formats at the same time. So he gives an example of zips or tars or gzipped tars, all kinds of different formats that he's talking about, and it just works. It just does what you would want it to do. But he loves the command line tool. He uses it frequently. But he, in his quest to contribute to it, to give back to the tool that has given so much to him, he encountered an interesting bug. So the bug is, the headline of it is, outputting text to the terminal increases runtime by up to 30%. So that's alarming. 30% just from logging is a big deal. And so he looked into it from the Ouch context and found that it really could be traced back to parallelism. Parallelism wasn't a part of the approach initially for this Ouch tool that he's using. It was added later. And when it was added, it caused a couple of problems that weren't immediately obvious. So first of all, having more than one thread fighting for printing info to the terminal caused dramatic slowdowns, he said. So he found that using two threads in parallel or two files in parallel. Individually, they took 31 seconds each. In parallel together, they took 49 seconds each. So that is not taking advantage of parallelism at all. And then he found out that it also broke the yes or no question about overwriting files. It asks the user, do you want to overwrite files? And when that happened, the logs would end up going out of order, and more than one question would be printed at a time. So they were both waiting for user input for the same time at the same time and things like that. So he gave an example of what it would look like. And the reason it was happening, he says, is because there's no synchronization between threads. So it was down to sheer luck about whether a second thread would print anything between the first thread printing a question and locking standard out to wait for user input. And that's a big part of the problem right there, locking standard out. In order to use standard out or standard error, you've got to lock it in order to write to it. And that carries with it a lot of overhead. So he points out that this is a common kind of issue when you introduce parallelism after the fact. He says it's often hard to anticipate what might go wrong when you make things run in parallel. And I've definitely faced that problem myself. So he goes into detail about what's actually causing the issue. When you print something out, like I was saying, you have to lock standard out or standard error. And locking isn't an instant thing. It's not a zero cost thing. It takes time that adds up. The more you're locking it, like if you're in a for loop, that compounds the effect because you're doing it over and over again. And if you're locking it from different threads at the same time, you might cause blocking as another thread tries to lock it and waits for the lock to succeed while the other thread is working on it. So his solution was just don't keep locking it all the time. Duh. I think it seems simple, but when you look into all that it took to go into it, it's definitely not. He talks about some different approaches that you could take. You could have a buffer of collecting messages that then logs it out after every X messages, or also every N milliseconds or something like that. But let's see. Yeah, so he found that just simply embracing that kind of approach, just flushing and clearing the buffer, also comes with problems because it halts all work and does nothing until the logs are printed. So essentially, the way that he figured out to sidestep all this is to run all of the log printing on a separate thread, which makes a lot of sense. It says our real work is no longer paused at all, since buffering a log message is just a vector insertion, and then printing it now happens on a separate thread. But as he points out, that can be a big change. It's going to require a lot of refactoring. And then one thing that you have to do in your application code is you've got to make sure you don't use print line. You don't use just the standard out directly. Otherwise, all of this work that you're doing is for naught because you're blocking everything anyway. So you've got to make sure that all your print statements instead go through the logger, which is good practice anyway. If you're writing a production application in Rust, you should avoid using print lines and things like that, and you should embrace a formal structured logger. So that's definitely good advice. He talks about what went into the out of order issue, talks about how he overcame the issue, essentially by being strategic about where the locking is happening. So in his case, they always have the prompt to overwrite the file, yes or no. So this is a place that is already locking standard out and waiting for input. And so let's do this in that same thread, he said, the worker thread. So he diagrams it all out to kind of convey how he set it up. There's the worker threads. The worker threads queue logger messages or queue messages for the logger thread. The logger thread is what locks standard out and flushes the logs, while the worker thread can do other things. And it seems like a really interesting setup. I like the thought that went into it, but it's surprisingly complex for just outputting log messages. There's a lot more that goes into some of this stuff than I think those of us who have worked in dynamic high-level languages for a long time, like myself, just don't even realize there's so much behind the scenes that's going on. Now, this next article here is something that is near and dear to my heart, really. I discovered dependency injection a long time ago in other languages, and I've really held on to it because it's really useful in ways that Peter Engelbrecht, a Rust consultant posting on the Chesero.me blog here, talks about. He highlights the benefits to it. I myself have my own dependency injection toolkit called Nakago that it was originally launched as a framework. Now I'm streamlining it and minimizing it into a more of a dependency injection toolkit that works with whatever framework you want. But it's definitely a topic that I have strong opinions about, and I liked the way that Peter approached it here. This is a very long article. Scroll down here, it's huge, so I'm not going to cover everything here, but I'll highlight a couple of points and talk about why I liked the article so much. But yeah, basically he talks about what dependency injection is. It's a design pattern that promotes inversion of control. So giving control for initializing dependencies, not to the code that's using the dependencies, but setting that outside and allowing a dependency injection container typically to provide the dependencies instead of it instantiating the dependencies directly. And that way you can use different versions of a dependency or different variants of a dependency without changing the constructor, the initialization code. But this is a problem in Rust because Rust doesn't have runtime reflection. And runtime reflection is something that is present in most other languages. If you're familiar with Go and its reflect ecosystem or tool, library, whatever it is, that's one example of runtime reflection. And TypeScript and JavaScript have libraries that provide it. But it's not really a compatible approach for Rust because Rust's priority is zero cost abstractions, and runtime reflection is it provides overhead. It causes overhead and is not zero cost. And there are some other downsides to it also that he'll talk about in a moment here. So like I was saying, instead of creating your dependencies directly, a component or a class, a struct, whatever you want to call it or work with, it receives its dependencies from an external source called an injector or a container. And the primary benefits are improved testability. This is the big one right here. You can easily mock and replace dependencies. You can isolate your dependencies down to whatever level of isolation that you want. If you want completely isolated unit tests, dependency injection makes it easy. If you want shallowly integrated integration tests, it helps. Or you can fully set things up for production or whatever deployed environment use that you want. And you can do it all in a way that does not change your constructors. Your constructors, your services are grabbing their dependencies the same way no matter what variant of those dependencies it's using. It decouples your components, so it encourages you to design things with interfaces and make things compatible and interchangeable, composable. It also helps with your maintenance. Like I was saying, if you change a dependency, it's not changing all the components that use it. It's using that interface, the trait that it implements, so that it's invoking it indirectly and giving you more flexibility about it. So he provides a really simple example here of a monitoring system. This monitoring system needs to use an email service and a data collector. But what if we need an email service based on Postgres and one based on DynamoDB? Or maybe we need one based on Redis if we have a temporary cache or something like that. Maybe we need a data collector that uses a different algorithm for this over here or something like that. So it's hard to do that in this directly instantiated approach here because if you want to test it, if you want to write automated tests, your email service is going to need your real credentials. And so I've been in situations where I've had to create a fake test account with test credentials just to sidestep this in an environment where I didn't have access to good dependency injection. So this allows you to inject a mock version of the email service for testing. It allows you to switch targets, switch platforms, switch all kinds of different things. So it's talking about, oh, what if instead of an email service, we need a Slack notifier or something like that. So he talks about how using an interface like a message service interface and a data collection interface allows you to implement the default version of that. So the email service would be the default message service, but then you could also implement a Slack service that would use the same message service interface. So then your monitoring system can just invoke the common methods defined on the interface, whether it's going to email, going to Slack, it doesn't care. It doesn't have to know. Maintenance becomes simpler. So this is something I strongly believe in. I use regularly in my Go code. I use the Samber do dependency injection tool that's based on the new generics in Go. But in Rust, this is an area where we've typically had kind of a drought or an absence. And a lot of people will tell you, you don't need dependency injection in Go. Or I'm sorry, a lot of people will tell you, you don't need dependency injection in Rust. They'll tell you that about Go too, but specifically, you'll see a lot of articles online saying dependency injection doesn't apply to Rust. That's not true. You have the same problems with instantiating things and ending up with big init methods that init all the things for this particular use case, and then another one that's copy and paste except for a couple of things here and there, etc., etc. It's the same problem. So Rust needs dependency injection just like any other ecosystem. And he points out a great article that I really like a lot, hexagonal architecture in Rust. I've seen a lot of people referencing this. This has definitely made a big impact, and I definitely ascribe to this kind of approach for building large-scale applications in Rust when you're going to have a lot of people working on it, especially, and you need varying levels of testing, units, integrations, full end-to-end tests, etc. It's really helpful. So it talks about how other languages like C#, he points out, might handle dependency injection. And the way that they're using it is at runtime through this runtime reflection. So like C# and Java say at runtime, they can look at the monitoring system to know which constructors that it has and what the arguments are for the constructors. And then it's able to, at runtime, so this is well after the build is completed, at runtime, it finds and it instantiates all the dependencies that satisfy the needs, the constructor arguments that it's reading. And you'll see some tools in Go that do the same kind of thing, that will use type checks or type guards to see which type of underlying concrete type this interface is representing right now. But in Rust, that's not possible because of Rust's commitment to zero-cost abstractions and avoiding things like runtime reflection and garbage collection and things like that that are common in object-oriented environments. So I think this is the right choice, and so does Peter in this article. It adds runtime overhead, like I was talking about. It adds to the binary size. And I think this is the most important one, it moves errors from compile time up to runtime. Now, I don't know about your project, but it's a whole heck of a lot harder to run my projects than it is to compile them. There's a lot of context that needs to be there. A lot of config and things like that it needs to initialize. If you have to wait until you have all that in place, generally you're waiting until your CI pipeline is running it, and you're not actually seeing the errors then. If with Rust's approach, it moves those errors up to the compile, the build phase, which is a lot lower barrier to entry at. You can get feedback a lot faster if it's in the compile phase, and you can make sure that it won't ever make it out to runtime if there's an error or a problem there. It also talks about how the Java approach, for example, is really implicit. It's really magic. It has to scan the entire code base to find all of the annotations for the dependencies it's injecting. And that doesn't apply to C#, and it doesn't apply to Rust either. And then the last benefit that he used is really an encouragement, I guess. With dependency injection, you can inject concrete classes. You don't have to use interfaces and traits. But I think what he's saying here is that it encourages the use of interfaces and traits so that your injected dependencies are actually interchangeable and you're getting some benefit out of the system. So the rest of the article talks about some of the considerations that goes into it. Like he said, compile time safety. The errors need to be compile time errors to maintain REST safety guarantees. One priority he gave was that the container should support lazy instantiation, which is something that my dependency injection framework Nakago uses as well. You don't want to initialize the dependencies as soon as you provide them. You want to wait until something requires those dependencies and then initialize it. And if you have dependencies that are unused, they won't have any impact on your runtime performance. So you can be a little bit less careful with the dependencies that you're providing because they won't actually be executed unless they're needed. It also talks about managing lifetimes is one of the difficult challenges here. And so in my approach is based on Rust's any type, which is dynamic typing, but which fits into the Rust ecosystem of compile time protection. So mine, the lifetimes are less important because anything that is any has to be static as well. So the lifetime doesn't expire. So mine kind of sidesteps that problem, but with obvious downsides. All of the dependencies in Nakago hang around forever. So he talks about that complication here and how you can have different lifetimes, singleton, scoped, or transient. So there's a lot of complexity that can go into a dependency injection framework. I tended towards simplicity on my side, but I really like that he goes into how to implement that. So anyway, this is where I'll step back. If you'd like to know the actual implementation that he recommends, you can read through the rest of the very lengthy article, like I was saying. But ultimately, I think it's a really good introduction to dependency injection, to the problem, to the underlying implementation and how complex it can be. And he says in future articles, he's going to talk about how to automate a lot of this using proc macros, which are really powerful. And he avoided in this first article. That's another thing that my Nakago framework also has, is a good set of macros to make this easier. So yes, take a look at this article, read through, understand how dependency injection works and what it could do for you, and I would highly recommend this one. Next up is a ghost story. This is from Maciek on his Flacum blog. Again, I probably pronounced that incorrectly, and I apologize if so. But it's a really interesting story that he posts on his blog. He had just released a new version of a legacy, the Rust application itself was a legacy Rust application. It was a safe HTTP interface for ImageMagick. ImageMagick does a lot of image manipulation. It's been around forever. So he was taking this legacy Rust application and migrating it to Kubernetes. Kubernetes is the container orchestration platform built by Google. And so it's based on Docker containers, and it can be a pretty big job sometimes to move things from a traditional server environment to a containerized environment like Kubernetes. And so after doing that work and deploying it to the Kubernetes stack, they got a message from their DevOps team, one of those panicked, hey, there's a problem. The application, they said, was scaling like crazy. They had a memory leak. So his first thought was, a memory leak in Rust? That's impossible. Rust can't have memory leaks. But he thought, okay, we are using ImageMagick, though. We're using the foreign function interface to interact with something separate from the Go ecosystem, essentially. And so he assumed at first that must be where the problem is. And then he also talked about gemalloc, which is another allocator, similar to what we were talking about on the RISC side. And essentially, he had some suspicions about where the problem may lie. And so he was sure that it was in the FFI code at first, even though the FFI code has been around for a long time. It's been very battle tested and hardened. But he thought he knew where to look for it. And so he talks about how he approached this, how he started to validate the memory leak and where it was coming from. He starts out from memleak from the BCC tools, but he couldn't really get it to work inside the Docker container environment. He could have asked the DevOps team to kind of set it up better, but as is often the case, the SRE team, the DevOps team, can end up being a bottleneck, and it's not really their fault. It's that they have so much that they're concerned with and owning. It can sometimes be hard to slot things in for the DevOps team in a timely manner. And so he wanted to leave that as a last resort. And that's a strategy that I often use too, is if we need DevOps support, we'll reach out to them if we have to, but we can often handle a lot of things on our own. Got to find a good balance in that approach. But anyway, he reached for heap track, which he's talked about in another blog post before, that traces heap allocations by tracing those malloc and free calls. So he had to add it, heap track and GDB, the debugger, to the container, deploy it, and then execute a shell inside the container so that he could use those tools and gather the data that he needs. He found out that they didn't have tar in the container, so they had to install tar. This is the trials and tribulations of containerized environments. But finally, he got some data that he could look at. And the data said, there's no memory leak. So already the memory leak is proving to be ghostly and unable to be validated in the way that he originally thought. So his first thought at that point is, am I seeing things? Am I going crazy? I have had those moments in development where I question my sanity because something that you're sure should do one thing does something else. And this is one of those cases. So he decided to, since it was using gemalloc, to use some profiling. There's a feature for profiling and leak detection that can be enabled at runtime in gemalloc. And so he ended up adding an additional endpoint that would help create that heap profile and check for leaks. He talks about how he did this, and then he compiled it all into a flame graph. And the flame graph showed there's no memory leak. So once again, his sanity is called into question. So he's realizing, okay, something's wrong. His assumptions aren't correct. He's not tracing the right things. So at that point, he talks about looking into how NixOS, the OS that they're using for really minimal images in Kubernetes, how to figure out how the memory is tracked. What is this monitoring system even listening to get the signal that there's a memory leak? And so looking in detail about how it calculates memory usage, he found out that the Grafana dashboard was not including the specifics that he thought it was. It was including the file cache. So even though he said earlier on that it said memory usage without cache, it actually is a memory usage with cache, but without the inactive file cache. So in his case, active file values or the cache usage is not a problem. It's a feature because they're relying on the file system cache to avoid duplicating the image processing. So the signal that they were getting was, hey, the cache is working. It wasn't, hey, there's a memory leak. It was, hey, the cache is working the way that we expect it to. But because of the kind of unclear labeling in Grafana, it wasn't very obvious that was where the problem was. And so he outlines here a lot of the things that he learned through the process. He calls out, more often than not, it's not the FFI code. The FFI code has worked for years. It's not that. There's all kinds of different things that it could be in situations like this. And the most important thing is to don't give up. Be persistent. Keep hammering away. This is a feeling that I have felt many times in production. It's like, there's a problem. It's really happening. You've got to find it. There's nobody else. You're the only one here that can do this. So keep at it. Don't give up. You can really, you can find it. I thought it was a really interesting kind of thought to check yourself when you're looking into production issues, because sometimes the production issue isn't what you think it is, and it might be something totally different that's malfunctioning. All right, so to wrap things up today, I've got two big project announcements. These are two projects that I really am interested in. I use SeaORM quite a bit. So SeaORM is an alternative to Diesel, the ORM for SQL that I was talking about before, that is synchronous. It was not built async first. So it comes with some of those challenges with different threads like we were talking about. And so SeaORM is an alternative to that. This is an async first ORM that does not have a synchronous process that it's communicating with via threads. It's async all the way down. So I really love the way that this works. I love the way that models are defined and the way that different operations are defined. And the 1.0 release that they are trumpeting here is a big deal. They're realizing that it's being used more widespread. It's even being used inside an application framework, the Loco framework, that really tightly integrates with SeaORM. So they think now is the time for a 1.0. Let's stabilize things. Let's stop making breaking changes and give people confidence that they can start building on this long term. So it talks about some of the changes that recently have been made on the way to 1.0. Talks about SQLite and other things, about this rename all attribute for changing the way that your tables are named, because they do some translation from the REST conventions to the database fields that you want, and this provides full customization of that. There's some other additions, other new features that are added to it. But really, the important thing is that it is stabilizing. It's not going to be subject to rapidly breaking changes. They're going to treat it as a 1.0 and move forward in a careful way to prevent those kind of breaking changes. And one of the things that it calls out is one of the underlying libraries that it's based on, SQLX in Rust, not to be confused with SQLX in Go. They had recently updated to 0.8, but they're keeping SeaORM 1.0 on 0.7, so that's going to be a fast follow to upgrade to 8, just to make sure that they're navigating the breaking changes in SQLX successfully. But yeah, they're excited that the community is building on top of it. They want to make that foundation solid so that we've got the confidence to go even further with it. And I'm really glad to see it. I think it's a great tool that you should check out if you haven't already. And then the other big project release is Tauri. Tauri is a native application framework for Rust that allows you to use common Node or TypeScript based front-end tools, so like React or others, to actually build desktop applications and increasingly mobile applications. It's really starting to look like kind of an all-in-one replacement to things like React Native or things like that, based on a really stable and solid and high-performance Rust core. So I'm definitely interested in this, and so their 2.0 release candidate, they went into it with the intention of mobile as a first-class citizen. So let's support mobile just as much as we support desktop. But after working on it for months, they really admitted that that was an overreach. They needed to back down a little bit, and that was over-promising. So they want to stress, it doesn't mean mobile is broken. It doesn't mean mobile is unsupported. They just haven't quite achieved the goal of it being a first-class citizen yet. There are still some things that don't work quite as well on mobile as they do on desktop, but they're pushing through. They're still going to work on those things. They're still going to pursue that goal of making mobile a first-class citizen in Tauri. That's just not quite there yet. They want to make sure you know you can use it for production. It's production ready. It's just not in full parity with the desktop yet. They talked about some breaking changes they needed to make for the 2.0 along the way. And I know, especially in Rust frameworks like this, the breaking changes are a very careful consideration. So they talk through how some of these changes are going to play out. So like one of the big changes they talk about is they've taken some of the core functionality that was baked right into it in 1.0, and they're splitting it out into different plugins. They're Let's see. Oh yeah, they've got a couple of other things. They've got a development server for mobile. They've got oh yeah, they took out a lot of the things that were public internally. So this is something that I sometimes get frustrated by. There's a library that I'm using and I want to replace something or use an alternate version of something, but they don't export the type that I need to do that or something like that, or they don't export the tool that I need to use within my alternate implementation. And I get annoyed by that because I want to remix. I want to combine and do my own things with it, but there's a good reason for avoiding it. There's a good reason for keeping things private unless they absolutely have to be public. And that's because of things like this security advisory that they talk about. The things that are public but don't have to be can end up being an attack vector. So we can't have nice things because of all the darn hackers. So that was one of the big things that is a breaking change, is reducing that surface area of publicly exposed things, markers, types, whatever. They also did an external security audit some time ago, actually, and they didn't talk a lot about the results because they wanted to remedy some of the things that were found. But now they've gotten things in a really good place. They're publishing the results of the audit, and yeah, it's a really good time to jump into Tauri. They're talking about how there are a lot of PRs and discussions that are open that they would love people to jump into and get involved with. So if you're interested in desktop applications using web technology in Rust, definitely check out Tauri. If you haven't already, take a look at some of the stuff that's out there for it. And if you are a longtime user of Tauri, you're loving what it's doing for you, then consider contributing and jumping into those bugs or discussions or things like that, and providing some value there. All right. Again, a longer episode. I didn't think that I would go on for so long, but I guess I've got to recognize that I ramble on. So hopefully you've enjoyed the articles that I've highlighted here. Like I said, if you have any feedback or suggestions for me, you can leave me a comment here, or you can find me on the Rust Programming Language Discord. If you'd like to work with me, I work with a great company called Nearform Commerce. We do especially e-commerce development, but a lot of other things too, kind of surrounding that. We're very specialized on the front end, but we've got a lot of back end chops too. And I would love to bring some Rust work into the fold, because I'd love to focus on that primarily. So if you've got some Rust work you need some help with, feel free to reach out. I'd love to connect you. And you can also find me on Mastodon. I've departed Twitter long ago in the Musk apocalypse, so check out my Mastodon. I'm going to start being more frequent there, so I'd love to talk with you there as well. Thanks for watching, and I'll see you next week.